excited for you to join us. If you've participated in the St. Petersburg Science Festival before, you know our next speakers. They are Mad Science. And Jeff Meister is going to be talking to you today, and his presentation is on fire and ice. So take it away.
Hi, everybody. I'm Jurassic Jeff from Mad Science. I hope you're having fun so far. I just wanted to open with some fun science today, and then we can get to some questions in the last few minutes. So I'm going to get started right off the bat. No need for rules today because you guys are out there and I am here. All right. So it just so happens I brought a friend with me here today, and his name is Mr. Egbert. Okay. Can you guys all say hi to Mr. Egbert? Mr. Egbert has a problem today, though, you guys. We've been in this pandemic mess for so long. We've been eating too much. We've gained a lot of weight. And he's got this great house that he likes to shelter in. Unfortunately, he can't fit in there anymore. I've tried to get him in there, and he's just too fat. So I'm trying to think of a way to get him in there. And I thought we could use science to get him in there. And so my thought was we could use the power of air pressure. And so what I'm going to try to do is, if I can reduce the air pressure in here, and air pressure is that air that sits on us all the time, it's always around us. So my thought is, if I could reduce the air pressure that's in the bottle there underneath Egbert, then Egbert's going to feel that enormous weight of air pressure on top of him, that 15 pounds on every square inch that sits on all of us all the time. We don't feel it because we're used to it. We have air and the insides of our bodies pushing out as much as it's pushing down. So Egbert feels that same thing. So I thought, well, air pressure is pretty strong. Maybe Egbert can get him from here down to there. So I need to do something in there that's going to get rid of the air in my bottle. And the best thing I could think of was fire, because fire needs oxygen, which is a big part of air. So if I can build a fire in there, I can reduce the amount of air in that bottle. That will reduce the air pressure in that bottle. And he's going to feel that relative weight of air above him. And it just might be enough to get him in there. You guys want to give it a try? That's what we're going to do. Okay, so first of all, I'm just going to get a little piece of paper. Okay. And what I'm going to do is I'm going to use that to light my fire down there. Okay. On that piece of paper, I'm going to drop just a drop of alcohol or two. That's going to make it burn a little bit faster. Go. And I'm going to light it on fire. I'm going to put it down in there, and then we're going to see if Mr. Egbert's going to reduce that air pressure. Come on, Mr. Egbert. There he goes. You see him go? Slowly but surely, he's going to get down in there. That's air that's pushing him. And there he goes. Okay? But I just thought of something. I got him in there. But now how am I going to get him out of here? Well, I tell you what. Because I need to get him out. We need to keep eating. So what I'm going to do is, if I used air pressure to get him in there, I think I can use air pressure to get him out, right? So I can do that by reducing the air pressure, putting more air up there than what's out here. Okay, so I'm going to do that just by blowing enough air up in there. And if I can get enough air circulating up in there, it's going to want to push him right back out again. Here I go. And then he comes back out again. Can you guys give a round of applause for Mr. Egbert? Thanks. He always comes through for me. All right, so that's Mr. Egbert. Another thing I wanted to talk about today was about energy and about this particular scientist, Mr. Einstein, okay? He's one of my favorite scientists because he knew about energy. He knew about energy and matter, how energy can be converted to matter and how matter can be converted back to energy. And he knew the enormous amount of energy that's locked up in matter, even tiny, tiny bits of matter. And that was through his famous equation. The amount of energy in anything, E, is equal to its mass, M, times C squared. When we square something, we just multiply it by itself. So C is the big number here. C is a speed, and the speed is the fastest known speed in the universe that we know about, the speed of light. So something really, really small, like this little piece of paper right here, that maybe weighs just a couple of grams, maybe half an ounce, okay? That's its mass. So the amount of energy in this piece of paper right here is equal to its mass times the c squared. And c, again, the speed of light is 72 million miles an hour. So if you take 72 million and you multiply it by 72 million, that's its square, you get an enormous number. So what Mr. Einstein was trying to say was the amount of energy locked up, even in very small amounts of matter, is enormous. We're gonna do an experiment that has to do with that now. We're just gonna take a little bit of energy, a little bit of matter, I mean, in the form of a liquid, okay? And we're just gonna put it in here, okay? So we're gonna squirt all that in here, okay? And then what we're gonna do is we're gonna shake it up a bit. And by shaking it up a bit, we are just gonna evaporate that liquid. So we're gonna evaporate means what? Well, it means taking that liquid in there and changing it into a gas. Now, this is a lighter liquid than normal. It's a type of ethanol, which is a type of fuel. Because it's lighter than normal, that means it's a little more unstable. And unstable in science means it can change its state, okay? So we can go from a liquid in there to a gas. And the more I shake it, the faster it changes its state. All right, now I'm gonna take all that matter that I got in there, and I'm gonna pour it right back out again into this cup. There it is. So you're gonna think, well, he doesn't have any matter in there. There's a tiny bit of matter there, and it's in the form of a gas, okay? So what I'm gonna do is I'm gonna release the energy in that tiny bit of gas now. Are you guys ready? Enormous amounts of energy. If you were here, I wish you guys were here, you can feel this. It's very warm, okay? So all that fire we let out, it's the same thing that happens in an engine of a jet. They spray gas in there, it evaporates very quickly, and they ignite it. That creates an enormous amount of thrust, okay? In science, this is the chemical reaction. We created fire by changing matter to energy. In science, we call that an exothermic reaction. Exothermic, because it creates heat. All right, so we've talked about fire a little bit. Let's talk about ice, something really cold. In fact, I have something really cold with me here today. It's not just normal ice, it's a special type of ice. We use it a lot here in Florida. They use it a lot on the coast. It's called dry ice. Now you're probably thinking, how can ice be dry? Because if we left that ice on that table there, then if we went out for a couple hours and came back, what would be on that table? It would be water. So ice changes its state. We just talked about it again. This goes from a solid to a liquid. We call that melting, okay? And if we left that out in the sun for a few hours, it would go from a liquid to a gas. That's evaporate, okay? So it changes its state. But this is a special type of ice. It's not frozen water, a frozen liquid, it's a frozen gas. So it's a solid right now, but in order to get this gas to turn into this solid, we have to get it way colder than normal water. You know what this is called, right? It's called a thermometer. It's a instrument we use to tell temperature. Scientists use centigrade C, and we normally see on the weather reports and everything else Fahrenheit F on this side. This ice, or normal ice, let's say, freezes at 0 degrees C. It boils at 100 degrees C. So centigrade is based on water, okay? But this isn't water. This freezes at a lot lower temperature. 0 degrees C is 32 degrees Fahrenheit. That's the freezing point of water. Let's talk about Fahrenheit. To get this gas to freeze, we have to get it to 110 degrees below zero. So here, there's minus 40. Keep going down, 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 probably like right here somewhere, okay? It's really cold. That's why I need to use these gloves. They use this in Florida a lot because we have a lot of fishermen in Florida. Fishermen like to keep their fish very fresh when they catch it, so they want to freeze it really quickly. Because this is so cold, it can freeze things very, very quickly. It would freeze my hand if I was holding this with my bare hand. It's very dangerous. So please don't play with this, or if you're going to use it, use it with adults nearby, and they can kind of teach you how to use it. What we're going to do is we're going to take this solid, we are going to change it to a gas, and that process is called sublimation, okay? It's not evaporation, it's not melting, it's not freezing. It's the process of going from a solid all the way to a gas and skipping that liquid state. So what we can do is we can take this, I'm going to break it up in a couple different little pieces. But we can take, actually, the first thing I'm going to do, I'm going to show you what kind of sounds dry ice can make. People that make movies don't like dry ice with metals because metals are good conductors. Heat and cold can flow through them, and so they don't like the sounds that dry ice can make. So if I just touch this with the metal, a good conductor, you see that it kind of makes spooky sounds. So they use this in movies. Again, metals conductors, heat and cold can flow through them. This is very cold. All right, so we're going to take this now. What we're going to do is we're going to put this ice in some hot water. That's going to sublimate it very quickly, okay? That's going to create that gas, that carbon dioxide, frozen carbon dioxide. That's what this, it's going to come up. To show you that gas, I'm going to put some bubbles in here. So we're going to create lots of bubbles. Okay? Let me try to find my hammer though. I just got it. I got some pieces in here. So if we take a piece of dry ice and I drop it in there, you can see that it's starting to sublimate in there, okay? Changing to a gas. I'm going to keep putting some more pieces in there. And we can create those spooky potions like in the movies, okay? And what I love to do is to take just some bubble solution and put it in there, and we create lots of bubbles, okay? And these bubbles are full of carbon dioxide. So they're actually a little heavier and they're a little stickier. So they're kind of fun to play with, okay? So frozen gas, carbon dioxide, and we're sublimating it to a gas, a liquid or solid, all the way to a gas again. Okay, lots of fun. Let me stick this over here, and we're going to do one final effect. I just talked about the movies and how they like to make scary sounds. What we're going to do is we're going to make that scary big fog. I don't know if you've noticed, but these bubbles are heavier, and the gas, when it comes out, it wants to sink towards the ground. Okay, carbon dioxide, what's that telling us? As good observers, as good scientists, that tells us that carbon dioxide is heavier than air. It wants to sink. People that make the movies know this, and scientists know this. So they use carbon dioxide or dry ice, frozen dry ice, to make those special movie effects to make that ground fog. So when I stick my dry ice in here, the gas is going to come out. It's going to sink towards the ground. I love Scooby-Doo movies, and in Scooby-Doo movies, they're always using fog. They're in haunted houses and the fog's rolling down the stairs, and the fog is in the graveyard they're always in, and they use dry ice to do that. So I have a bunch of dry ice here, okay? And I'm going to take that, I'm going to put it in, smash it up again, right? And then I'm going to put it in here, and we're going to see that big fog effect. You guys ready? And here we go. Right? And you can see as that dry ice comes out, as the carbon dioxide comes out, it flows right down towards the ground, okay? It wants to sink, it's heavy. What I love doing is kind of get it in here and scooping it up. And you see I have a hand full of fog. It's like I'm holding a cloud. I love holding clouds, okay? You can let it out, okay? So carbon dioxide, dry ice is frozen carbon dioxide. We sublimated it to a gas. Let me stick this over to the side. Wow, I got fog all over my house now. What am I going to do? Okay, that was some really quick science. Does anybody have any questions for me for Mad Science?
So Jurassic Jeff, we actually do have a couple questions already.
Yes.
So it's time for that question and answer period. So all of you listening in at home, keep in mind we do have around over 3,000 students participating in our science festival today. So we are going to do our best to try to get to all of the questions. If we don't get to your question, please still submit it. And what we're going to do is we're going to try to email answers to all of the teachers who have been participating with the festival. So there's a lot of questions about the liquid nitrogen. Can it hurt you, and what does it feel like? Like, what would happen to you if you got the liquid nitrogen on you?
That's a great question, David. Thank you. Actually, we're working with carbon dioxide or dry ice, not liquid nitrogen. Liquid nitrogen is nitrogen gas in a liquid form, very much colder than dry ice. Liquid nitrogen is about 345 degrees below zero. Dry ice, our frozen carbon dioxide, is only about 110 degrees below zero, but both can hurt you. Okay, they're both colder than anything we see on Earth. Okay, so you always want to use a glove. If you ever got some on you, it's interesting. Something that's really cold feels like something that's really hot. It's going to feel like it's burning you, and it leaves a little burn mark on you. Okay, so you always want to be very careful with. Always handle it with gloves. And if you do touch it, you can touch it very lightly, very quickly. But I do it sometimes, but I'm trained on how to do it. So it's very dangerous. Never grab a hold of it. Never touch it. Always use gloves with dry ice. Liquid nitrogen in particular, because it's so much colder.
Awesome, thank you. Now we do have a couple other questions with the dry ice, and one is, how is dry ice made?
Great question too. Because it's a gas, they can't just put it in the freezer and expect it to freeze like water. It's 110 degrees below zero. So what they do, they put it in these big machines. There's a company over in Tampa called Airgas, and they make dry ice over there. What they do, they put it in these big machines. They lower the temperature really low, like 110 or 120 degrees below zero, and then they start to compress the gas, and they compress it, and they compress it, and they compress it. So it takes two things, very low temperatures and very high pressure. And eventually that gas starts to turn into a solid, and it turns into dry ice.
So how long would that chunk of dry ice last? If I just had it out there, how long could that last for?
A great question. People think they can save dry ice by putting it in their freezer. It doesn't last any longer in the freezer than it does out here in normal air. This piece of ice right here would probably sublimate in about 4 to 5 hours. So it lasts a lot longer than normal ice. A normal piece of ice, that would probably be melted within an hour. I'd say that piece of ice, probably 4 to 5 hours. I can keep dry ice overnight, but it probably loses about 10% an hour of its mass.
Awesome. Well, we saw that it created a lot of those gases and the fog. Is that fog dangerous at all, and can that hurt you at all?
Not really. The fog, and this is the interesting part about it, is not so much the carbon dioxide itself. The fog is created because of condensation, okay? And that's because the ice in there, in the water, is cooling it off so much that that air around the water is instantly getting colder, okay? And dry ice is kind of odorless. You really can't, it's not that dangerous for you. But what happens is that air cools off so quickly right near the water that you put the ice into that cool air cannot hold as much moisture as warm air, and that's how clouds form. And so it condenses to form that cloud, okay? And there is some carbon dioxide in that cloud, and that's what makes it heavier once it makes it to sink towards the ground.
All right, Jurassic Jeff, we're getting a lot of questions about one topic. And we know we love to touch things. There's lots of questions about if you were to actually touch that dry ice with your hand, what would happen?
Your hand would be, it'd be like touching fire. Your hand would get burned, okay? It'd leave a burn mark on you, just like touching fire. Something very cold reacts to your skin like something that's very hot. It's called freezer burn or frostbite rather than a regular kind of fire burn. But it's gonna leave the same type of mark on you, and it's gonna hurt.
Is there any way to actually melt dry ice into a liquid, or does it always go directly from a solid to a gas every time, all the time?
Great question. Again, dry ice doesn't melt. They call it dry ice because it never gets wet. It doesn't melt. Melting is the process of going from the solid to a liquid. Dry ice does not have a liquid state. So it always sublimates to a gas. That process is sublimation, going from a solid, skipping the liquid state, all the way to a gas. Because remember, dry ice is not a liquid. It's a frozen gas. So it only has two states, unlike water that has three states.
Okay. So can you get creative with the dry ice? Can you put different colors in it? Are there different types of dry ice?
Yeah, for Halloween we do that. There's only really one type of dry ice. Dry ice is frozen carbon dioxide, but we can make different colors with it. Okay, and even though the colors they still make kind of the white cloud, it can get a little bit colorful with the different types of fogs that you can make. So we got to do that for Halloween type stuff.
So if you put dry ice in the sun, does it sublimate any faster in the
It
sun?
does. The sun, any direct sunlight's going to warm the temperature. The warmer the temperature, the faster the sublimation. You notice that when I put it in hot water, how fast it sublimated. It sublimated really quickly. That's what creates the cool effect. So the warmer you get it, being in hot water or the sun, the faster it's going to sublimate or change from a solid to a gas.
So we're also getting a lot of questions about, can I do this at home? And if so, where can I get it? Because you're talking about Halloween a lot and it's used for a lot of these movie effects.
It
So,
is. Yes, you can get it. You can get it at Publix's. We get there is a number of retailers around that sell it. Okay, Publix is probably the main place that we get our dry ice. Okay, you just have to call around to the Publix near you and ask them if they carry dry ice. But again, they're only going to sell it to adults. So you work with your parents to get dry ice, and they can supervise this with you. Okay, so you can kind of work with yourself. You can create a lot of those cool Halloween effects for Halloween. It is hard to get right before Halloween because everyone's trying to buy it. So maybe pick it up a day or two before. We just put it in a cooler like this, and it keeps a little bit longer. But it is fun to work with. But just be careful. It is dangerous. Always have an adult with you.
all right, so I want to turn a little bit. We're getting a couple questions about the fire because that's also generating some questions too. So, how did you not burn your house down? You had an explosion inside your house. How did you not burn it down?
That's because I'm a trained mad scientist. We've done this hundreds, even thousands of times before. We know what works. We know that these bottles will hold the fire very well. Okay, it only burns for a couple of seconds, okay, or even like a second or two. So we've never had anything explode on us yet. We always practice safe science at Mad Science. We always test it, and we will, again, we always kind of know what we're doing. So I don't do any experiment that I know is not going to be safe. We always try to practice safe science. So I knew that was going to happen. I knew it was produced, and we've never had any problems with this before.
So, how did you learn to be a scientist? Like, how did you learn? Like, how do you practice this? You're playing with fire and there's an explosion. You really don't want to mess it up too many times. So, how'd you learn how to do this?
Well, I'm a trained scientist. I used to be a geologist before I became a mad scientist. That is an earth scientist. And I love science so much that I decided to start Mad Science for Kids and show them how much fun I had with science when I was a kid. But you learn these experiments. We learn these experiments through different methods. We see them done before, and then we work with it and we practice like anything in life. If you practice, you're going to make sure it's safe. Okay, and especially safe in front of you, and if you're doing it in front of kids and families. So we always practice. We plan our science. We do the experiments back in our lab, make sure that everything's safe and that we know what we're doing and we get the effects that we're looking for. But it's like anything, if you want to be a good scientist, you've got to practice, but it's so much fun. It's so much fun to do.
So, how do you control how much fire then is actually made and how big the explosion is that comes out?
By the amount of liquid I put in it. And if you notice, I kind of sloshed it around everywhere. When I sloshed, I tried to get it on all the surfaces and that evaporated. And then I poured it almost all back out again. If I would have left the liquid in there, it would have burned a lot longer. It probably melted the bottom. We know to pour everything. There is a tiny bit of liquid in here. In fact, I can see it, okay, right there. Okay, we try to get all the liquid out, okay, because we know it's going to keep burning in there. This is a very flammable liquid, ethanol is, that's what we use. We know we try to get it all out of there. That's going to be a lot safer than leaving much of it in there at all.
And unfortunately, we still have a lot of questions coming in. We're not going to be able to get to all of them. So we're going to keep track of all the questions, and we're going to get answers to the questions, and we'll send them
Sure.
out to everyone. One real quick last question. How cold is the dry ice? What's the temperature?
It's 110 degrees below zero. So we talk about the Arctic and the Antarctic a lot, okay? And those are very cold places, but no place on earth is as cold as 110 degrees below zero. We know Florida is a pretty warm place. It barely gets to freezing, which is 32, which how cold it has to be to snow. And that's right about here. So think 32 down to 0 degrees, okay? Which is right here, down to minus 40 degrees below zero. We've got to go 60 degrees lower off this thermometer to get to 110 degrees below zero. It's pretty super cold. And that's what it has to be to make dry ice.
Wonderful. Thank you very much, Jurassic Jeff. It's been an exhilarating experience. Loved it. Thank you again. And for those of you listening at home, thank you very much for joining in for the session. Feel free to stay on for our next speaker in track B, or feel free to move over to track A. Thank you again.
Thank you,
and have
David,
a wonderful
and thank
day.
you all, and I'm happy to answer any more questions if you want to send them to me or write them down or visit our website. Thank you all. I appreciate being a part of the Science Festival.
Bye-bye. Thank you.